recalcitrants in their seats. And if you want to light her up, we'll get started. Okay, good evening, everybody. Welcome to the Amateur Radio Experimenters Group's October General Meeting. I'm very pleased tonight to bring everybody a special guest of ours. We've invited Roger Harrison, VK2ZRH, to come and talk to us about a subject he knows well and dear, and that we're all incredibly curious about, which is ionospheric propagation on 6 meters or 50 megahertz. Thank you very much, Roger, for making the time this evening to speak with us, and I'll hand it over to you. Thank you very much.
Well, thank you very much. Here we are, ionospheric propagation on 50 megs. So, a subject dear to my heart since I was a teenager. I won't show the picture. So, we're going to be, I have to limit it to sporadic-E, TEP, and F2, long-haul DX on 50 megs. There are other modes, but we'll leave that to another day perhaps, given that there's a time limit. If you have any questions on the way through, please say them towards the end. Write down the number of the slide, which is on the lower right-hand corner, and we'll see what we can do in the follow-up. So the following presentation is non-fictional and definitely depicts actual situations and events. Radio amateurs are warned that images and diagrams may depict DX that has been missed. One morning, listening idly on 50.15, quiet noise, whack, CQ, VK4XX, S9 plus, deep fade to S2, back to S9, then whoop, silence. A weak VK7 calls VK4. Ever noticed that? Our experience of sporadic-E propagation on VHF. When the band opens, it's often chaotic. Propagation may jump from area to area. Stations a few kilometres away work others you can't hear. The MUF might rise over hours or only minutes. Signals can appear and disappear suddenly, may only last minutes or for hours on end, are often strong, punctuated by deep, rapid fades. Sometimes appear from unexpected directions. Every sporadic-E propagation event is different. So, you need a little refresher on the ionosphere. Here it is. At night, all you've got is the E region and the F region. In the day, you've got the D region, the E region, and the F region splits into F1 and F2. The gaseous ions that are there are only nitrogen, oxygen, and nitrous oxide. This becomes important later. So, a little more background on the ionosphere. So you've got the exosphere, the thermosphere, the mesosphere, the stratosphere, and the troposphere. We live right at the bottom of the troposphere. And most of what goes on in our area has little effect on what goes on up around where that T sits. The electron densities look like that pregnant man at the top right-hand corner there. And you get electron densities 10 to the 4th up to 10 to the 6th. It can go greater per cubic centimetre. So where does sporadic-E sit in the ionosphere, in the atmosphere? Here's an overall diagram that gives you the red zigzag is the temperature. So that runs from the 20s and 30s right at the down below the tropopause, and plunges to minus 50 once it gets up above Mount Everest heights, but comes up again to zero around the stratopause in the 50 to 60 kilometre range, and then declines again around the minus 80s or so once it gets to around the D region 80, 90 kilometres, and rises from then on upwards. So there's a couple of places there, the mesopause, the turbopause. The turbopause is where the atmosphere begins to come apart at the seams and separate into the separate gaseous components. Sporadic-E is an alien in the ionosphere. It's not related to the E region at all, other than that's where it appears. It's not excess E region ionisation. At mid-latitudes, Australia, New Zealand, for example, North America, Europe, sporadic-E is thin, dense clouds of metallic ions and free electrons from less than a kilometre thick to around 5 kilometres thick, maybe. And they're lying at heights ranging between 95 and 150 kilometres. It can comprise one or more clouds or patches. They might be continent-sized, thousands of square kilometres, or only 100 metres in diameter. And the ions that are there is iron, magnesium, and calcium principally, the detritus of meteors. Here we are on patches. That gives you some idea of the scale of the size that you can get, sometimes much bigger. This, of course, is from the drawn over the horizon radar. So when we look at the electron density in terms of altitude, you get a diagram like this, basically from rocket measurements. So how does it happen? This complicated diagram shows that ions blown down and across the magnetic field at an angle and upwards, eastwards, across the magnetic field at an angle will bunch in a very thin layer. And the electrons, all the electrons that are free electrons that are around, follow the positive ions. So they're dragged along into the same thin layer. So the wind shear theory, this is it. Professor Whitehead and another guy called Axford put this together. So there's your equation. The interesting thing is that there, if you see on the top part, the hi cos theta, that's very important. H is the strength of the magnetic field, and I is the angle at which the ions are blown across the field. It typically takes 100 seconds to compress the ionisation. And Whitehead says if the process was perfectly efficient, sporadic-E layers would only be 100 metres thick. But of course, nothing's always that efficient in nature. So, things to note. Left to itself, a sporadic-E layer or cloud will disappear in a few minutes as the ionisation would disperse by diffusion. That is, it would just get knocked around and dissipate from all of the bumping of the atoms in the atmosphere. The wind shear ensures continuous formation of sporadic-E. It doesn't form and then just sit there. If the wind shear stops, it dissipates, and often quite quickly, even if there are large changes in the horizontal winds. Wind shears occur both day and night, so sporadic-E occurs daytime and nighttime. Wind shears sometimes stack one above the other, and thus you get two or more thin ES layers form, separated by perhaps 2 to 10 kilometres. Here we are, some rocket measurements with stacked sporadic-E. You get some pretty hefty electron densities there, particularly on the right-hand side. So the life cycle of ions, and This is quite important. There's only a comparatively recent finding. So meteor ablation leaves dust behind. And photoionization and charge exchange will ionize the remnants of the meteor dust. And the ions drift through the upper ionosphere and then down to lower latitudes in what's called a fountain effect. Neutral winds blowing east and west will make them converge. The same process occurs with magnesium ions and to some extent calcium. So you get descending sporadic-E layers occurring. I'm having some trouble with my screen here. It's doubling up. The ions and associated free electrons motions are guided along the geomagnetic field by the Lorentz force, if you know your magnetic physics. Here's the life cycle of ions. So it's dependent very much on altitude and, of course, the electron density. So it can last from a number of hours up to a number of days, best part of a week. Oops. Here we go. And here's that fountain effect I mentioned earlier. They drift southwards from the equatorial region down into the mid latitudes, and of course from the northern side up northwards. So mid latitude sporadic-E. The orange lines. This is a sort of an idealized diagram showing the geomagnetic latitude. So the mid latitude is specified as between 10 degrees and 60 degrees geomagnetic latitude. Now, tides and gravity waves. Oh dear, this is remarkably complex. You get solar radiation drives the global thermal tide, so it heats up the atmosphere on the sun side, in the morning and through the morning, and the thermal tide moves away from that in both directions, curiously, and northwards and southwards. At the polar cap, thermospheric winds there push winds southward in the northern hemisphere and northward in the southern hemisphere. And you get those little jiggles called gravity waves, which jiggle the atmosphere. The atmosphere is just is actually a real soup of all sorts of bubbles and waves. So the thermospheric winds there, they excite what are called planetary waves, which have periods of 2 to 16 days. So they spiral around through the atmosphere around the Earth. And of course, gravity, think of buoyancy in terms of gravity waves from atmospheric shocks and ripples. So you also get large vortices, just like you see with weather systems. Once you get up into the thermosphere, you get these large vortices. And in the E region, in the neutral atmosphere, this knocks all of the ions into a into a sort of like a corral arrangement in the center of those vortices. Then the atmospheric tides and planetary waves and gravity waves combine to generate wind shears that create sporadic-E. You've got to line up all of these ducks in a row just before you can get a sporadic-E event. Then, of course, there are seasons to it. The meteor dust input is seasonal, and it's different in the southern hemisphere to the northern hemisphere. So when you sort of put together some measurement of a mid-latitude sporadic-E MUF and combined with graphs of the planetary wave winds systems, you get this, lining up, etc. So there's quite a bit going on there. So the influence of planetary waves you can see in the ionograms. You're all familiar with ionograms, I presume. We'll have to presume that. So I sat down and took a month's worth of ionograms every half hour and measurements where the sporadic-E occurrence was greater than 10 megs, or 9 megs, so that you would it was likely to support 50 meg propagation. And then I mapped it all out, thousands and thousands of points, and you can see, you can tease out a bit of the different gravity waves there. It's rather like spectral management or spectral view of something happening very slowly. Now, having some trouble with my, damn it. This is not working. Pardon me. Better. So here's a seasonal view of sporadic-E in ionograms with values greater than 5 megs, which is generally termed strong sporadic-E. So here it is through the summer of 2 years and the times. So you get this really odd effect. You can see a peak just before local noon, and then patches all over the place, and then it repeats itself the next year. So if we look at some local results, Brisbane, you get this, local time versus month of the year, etc., for over particular years, about a decade. And Norfolk Island and Canberra, you can see similar patterns. So you see the diurnal pattern there and you see the seasonal pattern there. There are some similarities, but every one is different. And if you do it for a different year, it'll be different again. So sporadic-E and the solar cycle. Now, this little diagram shows two propagation paths experiencing the opposite occurrence rates for high versus low solar activity years. The dotted lines represent percentage occurrence of sporadic-E likely to support 6 metre propagation. And on the left-hand side, high solar activity, path A and path B are quite different. The occurrence rate on path B is much higher than path A, whereas, go for the lower solar activity year, and it's the other way around. This is a bizarre outcome. Okay, so ionograms. So here's a classic sporadic-E. I'm having difficulty. I'm sorry, I'm pausing. I'm having difficulty reading this because my screen is writing one view over the other. So this is the classic sporadic-E. This is likely to, because to propagate 6 metres with Brisbane as the centre point, and it's blanketing the F layer. So this is quite large, covering the view of the ionosond. So propagation via that is very simple, straightforward. There's the equations. I've had this in AR. You can find it. Again, it's actually online these days. When you look at the geometry, you get the ordinary M factor if you know your propagation characteristics. So it's important that the angle B, which is the top left there, determines the MUF. I've killed it. Come on. That's better. And when you map it out, ray path elevation versus different heights, this is what you get. So if the ionogram shows top frequency of 10 megs, you can get 50 meg propagation at low angles from various heights. So this gives you a good arrangement. Now remember this because it comes up again shortly. So here we are. I showed you plane ES. So this is spread ES. So it's rippled or crinkled, as Whitehead was wont to say. And it's in patches, so you can see through it. So you can see the F layer through it. And the top frequency, FTES, is important because that determines the maximum usable frequency. So here's propagation via spread ES. This is a bit different. Now the crests on the ripples are only, a couple of 100 meters up to maybe at the best 10 kilometers apart. How do I know this? I've read all of the papers. I've seen all of the tomography of what's going on up there. Now here's your M factor. It pretty much doubles once you get spread ES. So you may not have a very very dense sporadic E layer, but the MUF can be quite high, and it's that which supports most of the time supports 2 meter propagation or 100 meg propagation on the FM band, for example. Now, how do we get such strong signals? Well, one of them is that sporadic-E provides what they call specular reflection. In other words, mirror-like. That's the general ionospheric physics term. And you also get focusing. And this is one of the mechanisms of focusing, in that the layer gets denser towards a peak and then declines again. And so you get a different turnover in the layer. And so you get a focal point on the ground. How do I know that? I've driven through one. And with spread-E, you get this sort of effect with ripples, which again causes focusing. You can get path loss, which is which is less than, very much less than free space path loss. So across the world, you've got geomagnetic control. If that magnetic term is in the wind shear equation, it works better in some places than others. It's really poor over South Africa and the South Atlantic, you can see. And it's really good over Southeast Asia or South Asia. Now you can see there some marked points, K, B, W, and C. So different things happen with sporadic-E at those different locations. At K, that's Kokubunji in Japan, and Wakanai, also in Japan. They're not terribly different in geographic terms between those two, but there's quite a difference in the number of hourly observations of showing sporadic-E greater than or equal to 10 megs, which of course supports 6-meter propagation. And B is Fort Belvoir in the US. And C is Christchurch in New Zealand, of course. So it does rather better than Fort Belvoir. Now, of course, in recent years, decades, measurements using satellites, occultation of 1.5 meg signals, enables measurement of sporadic-E occurrence. I got this from a scientific group headed by, I've forgotten the name, Aris, in Europe. So you can see the geomagnetic control there, the paucity over South Africa, and the density over Australia, the Tasman Sea, and the South Pacific. Now this, of course, is summer, and so there's not much sporadic-E in winter. Here's the Northern Hemisphere, vice versa, swapped. So same sort of things apply. You can see quite a lot over the North Atlantic and Europe, of course, and North Africa, and of course the North Pacific, but less so over the US and Canada. So multi-op sporadic-E propagation, does it happen? Well, here it is. Lots of people thought that multi-op sporadic-E couldn't occur because it was just you had to line up too many ducks in a row. Sorry, folks, here it is. This, of course, is the chirp radar of Andrew, VK30E, VK30ER. The interesting thing about this, of course, as you can see, the big peaks of the multiple hops, but it fills in between, which suggests that perhaps with more sensitive digital modes, you can go a lot longer, a lot more places in between the major hops. Here's the ground view, or shall we say the satellite view of that last one. And so that goes well out beyond 4,000 kilometres into the Pacific. Now, here's something from what was the earlier VK logger, 6 metre spots. You can see the big one across Mexico to VK4 and Peru, that's OA4TT into VK2 and VK4 over quite a long window. And this is the contact between OA4TT and 2FLR, for which I managed to get all of the appropriate parameters to analyse the path. And interesting thing is, there are different hop lengths over different sectors of the path. It's rather shorter in the sector from Australia to the other side of New Zealand, and then it stretches out across the South Pacific. Now, we have another feature in the ionosphere called the equatorial ionospheric anomaly, EIA. This is created by the sun, heating up the F layer, F2 layer, exciting all of that ionisation. So you get quite a substantial increase in the total electron content from solar radiation. Naturally, of course, it follows the sun westward across the planet. And the best shape and intensity occurs at the equinoxes, because the sun is in a better position in regard to the geomagnetic equator. So you get mixed sporadic-E and F2, otherwise known as N mode propagation, along the lines illustrated here. Again, 3OER and his chirp radar. So this is into the North Pacific, well, actually the West Pacific, across Papua New Guinea. So this sort of mode is called N mode for obvious reasons. It's sporadic-E, F mode, via the equatorial ionospheric anomaly. You can get a single hop via that of 4,000 kilometres, and that will support 50 megs on more occasions than you think. So here we are, an illustration of it. I've put those rings there to indicate the southern equatorial ionospheric anomaly. So out to 5,000 kilometres or so for that big peak of reflection. Moving on. Notice the location of midday. So we come to transequatorial VHF propagation. Here's where we cross the equator. The afternoon type is experienced predominantly between 1400 and 1900 local mean time relative to the path midpoint. Evening type predominantly occurs between 2000 and 2300 local mean time, again relative to the path midpoint. So, referred to each by their mode of propagation. In the top, we have afternoon type ATEP. You can see that it's reflections via tilts in the ionosphere at the EIA without intermediate ground reflection, whereas evening type is via bubbles, equatorial plasma bubbles that rise in the ionosphere. They're very large. And the EIA is no longer there. That dissipates after sunset on the ionosphere, and you get an instability called a Rayleigh instability, which causes ripples, which then rise up and form these bubbles. Afternoon time is called supermode TEP. Propagation involves two F-layer reflections, north and south of the geomedian equator, without an intermediate ground reflection, as I said. Caudal hop. A lot is said about caudal hop propagation, and most of it is BS. Maximum observed frequencies typically of 40 to 55 megs, up to 60 to 70 megs on some occasions. Path lengths range typically from 4,000 to 10,000 plus kilometres, hence being able to cross the Pacific. Often strong, steady signals with only small Doppler shifts. Peak seasonal occurrence is equinoctial, and the occurrence rate follows the solar cycle. With ATEP, here is a recording I made in Townsville back in 1972. So that shows you the sort of signal strength and Doppler shifts you get. So with evening TEP, it's called ducted mode propagation. If it's going up and down those tubes, of course it's called ducted mode. Propagation is via ducting or gliding through the equatorial plasma bubbles, which are field aligned, depleted ionisation, which thread the nighttime equatorial ionosphere and extend symmetrically north and south of the geomagnetic equator. Path terminals lie close to near conjugate areas aligned at narrow angles orthogonal to the geomagnetic equator. Maximum observed frequencies often extend to 144 megs, sometimes to 432 megs, but no two-way contacts have ever been reported or recorded. More's the pity. This coming solar cycle peak, you know, we could make a concerted effort and actually do that. So here we are looking up a cross-section of the ionosphere, looking up the tubes. So here we have TEP with ES extensions. You can add one to the other and get really extensive propagation. A lot of people thought for many decades that this was not possible, that one could not follow the other, but it does, and I've done it. So here's a better than classical one, recorded by Andrew 30E. So the big peak is reflections from that rough mountain area in New Mexico known as the Ponderosa. Of course, cue the theme song from Bonanza, if you're old enough to remember it. On the west coast, of course, that's a reflection from Catalina. There's, of course, quite strong, tall cliffs, that part of the coastline of California. So cue the Beach Boys. And on the other side is a rough area, kind of hilly, around Clarksdale, Mississippi. So, cue Crossroad Blues from Robert Johnson. Now, 5 BC extended himself and worked IW9HII in Sicily, in a village called Gibil Manor. It's distinguished itself by having a very well-preserved church there. So I managed to be able to get sufficient ionospheric parameters from ionosons at the time to be able to analyse the path, the propagation path. But as you can see in the lower slice, it might be sporadic-E across those last between E and F, or it might be F2 via the EIA on the north side. Too difficult to distinguish without having some path delay data, which of course wasn't able to be obtained. Now, prospects for round the world on 50 megs. Yeah, back when Sputnik was launched, it transmitted on 20 megs and 40 megs. And 40 megs was heard when the satellite was well below the horizon. Not only that, it was the opposite side of the Earth, but it could be heard with quite strong signals. Remarkable stuff. So here we have the ionosphere. This could be F1, F2, or thereabout, lower F2. It's called guided mode. And numbers of instances have been recorded. You need to line up a whole bunch of angles in order to get into it. It's not a whispering gallery. It's more like a leaky hose. And the seminal paper which explains it comes up with a series of diagrams like this. This is the middle one for the mid-solar cycle. However, as we're coming up with solar cycle peak, what would happen here is that the three peaks at 25, 30 and 40 megs move upward and to the left, and 50 and 60 megs move upward and to the left a bit, which improves the chance of propagation. Does it happen? Yep. Andrew has a recording taken at 28 megs of around the world propagation out to 4 times, 3 or 4 times. Not bad.
SFA.
Hello, Roger. Thank you for the presentation. Slide 58, if we could go back to that. So it's the Adelaide to European circuit.
Let me get that up again.
Yep, no worries.
Yep.
Excellent. Could you tell us what time of the year that was and what time of the day that was in Adelaide?
I thought I had it on there, but it was late summer.
Right. Okay.
And of course, time of day. I said I've got local time, right across. wherever you're looking at, you know. So Brian, it was, you know, after 1600.
Yeah. Okay. Yeah. Okay. So that was in summer. Over the last couple of years, not this year just gone, but the year before, we had some spectacular openings into Europe in our winter, and a lot of active amateurs on 6 Air. The happy hunting time last year. This year was pretty much a fizzer, but I didn't realise there was just going to be so many hops involved here to get from Adelaide to Europe.
Yes. Well, the thing is that you've got specular reflection, so from the sporadic-E, so very little loss there, if any. And remarkably, the loss from ground reflection is only, you know, 2 dB, 3 dB at worst. So I've got a in Kenneth Davies' 1960s, 69, 65 book on ionospheric propagation. He gives a nomograph to calculate it all, and I've extended the nomograph, fleshed it out fully, and made the connections, and sort of the, you know, the total path loss is better than it is on 20 meters by, you know, a good dozen or 15 dB. So, you know, you're going to get 3 or 4 S points out of it.
Okay, so it's probably worthwhile this summer, I guess, heading into the solar maximum over the few years to be aiming at Europe in the summertime.
And the wintertime.
Oh no, wintertime given that's a known thing. I've just never heard it to be the summertime. Normally,
yeah. The thing is that Brian repeated that contact exactly 10 years later to the day. Now, what does that tell you? It tells you that the ionospheric weather, the neutral atmosphere weather, all those planetary waves, in particular, are cyclic to that extent.
Very good. All right. Do we have any other questions here? Okay. Do we have any questions from any of the members on Zoom as well? If you do have a question, just unmute yourself and just announce your name and call someone. Okay. Do we have any other questions at all at this end? All right. One last call for anybody on Zoom. I'm not sure, Hayden, if there's any questions come through on YouTube, but if they are, if you want to pass them through as well. Looks like we've got one. Okay, well, I think that's probably it for tonight, Roger. You've stunned them all into silence, and they're all pondering what it all means now. But thank you very much indeed. Thank you very much for your efforts in putting it together and for making the time for us this evening down here in Adelaide. So a round of applause, please, everybody, for Roger Harrison. Thank you very much.
Pleasure. Thank you.